Okay, let us start. Our second speaker is Alexander Veselov about the Painleve-I equation and Masur-Veech volumes.
Okay, thank you very much. So this is quite an old story for me, at least, and so it started when I visited my first visit actually to UK, and I visited John Gibbons in Imperial College, and we discussed dressing chain, which was proposed by Shabat with a view to apply it to spectral theory. And there was quite natural variation, I will explain, one of the closures. And we spent some time with John trying to find solution of this equation without much success. And then Alex Stokes came to visit me in Loughborough. When was it? It's during the COVID, actually. So it was not a long visit, but we started, and I asked what he is interested in, and he said delay equation, and I said that, oh, I know one delay equation which we studied with John Gibbons, but failed. But now I know how to change the question, because probably what we were looking at doesn't exist actually. So that's why we failed. So, and we started to consider formal solution rather than real solution, because for spectral theory, you need a real solution. And formal series solution is cannot be applied to spectral theory. But anyway, we studied with Alex, and then for a couple of years, we had a problem what it is related to. If it's not spectral theory, what is it for? And it turned out to be related to very interesting area related to Teichmüller theory, namely with the calculation of Masur-Veech volumes. I will explain this, and then I will. And that was a kind of luck, because it gave a very nice interpretation of the object. We felt that it must be important. So this is the paper now accepted in Journal of Geometry and Physics. So what a dressing chain? Dressing chain is sequence of Darboux transformation. It was mentioned in the previous talk. And but this is specific Darboux transformation applied to one-dimensional Schrödinger operator. And the transformation is actually you factorize it and then swap the order and adding alpha. And Shabat considered sequence of this, infinite sequence of this transformation, and they described what we call dressing chain. This is dressing chain. It's first order ODEs, infinite sequence of first order ODEs. And he found some interesting spectral application, spectral theory application. And we later looked at periodic closures. And that was quite nice, because in this way, we found alternative way what I studied as a student, finite gap theory. I was a student of Sergei Novikov, and finite gap theory was very hot topic at the time in Moscow. And so what is called Novikov equation of stationary KdV hierarchy, which turned out to be have very special, very interesting relation to spectral theory, also linked with algebraic geometry, namely hyperelliptic curves. So, and we kind of recover the same theory, but from a different point of view, namely stationary KdV is stationary point of isospectral flows, and here it's kind of discrete version because we going across every time we add in alpha, and if sum of alpha is 0, some kind we coming back to the same, then we have finite gap theory. But if sum of alpha is not 0, then we up, and we have generalization of harmonic oscillator, because they will have the spectrum which is not one but several arithmetic progression. For harmonic oscillator, for n equal to 1, we will have just arithmetic progression, standard spectrum of for the harmonic oscillator, which actually was derived by Schrödinger exactly using this way. So this is, but for n equal to 3, for example, you have new examples, variation of harmonic oscillator, quite peculiar, which are also which has spectrum consisting of 3 arithmetic progression. So that was thing. And our idea was John Gibbons was, let's look at we thought that what if we do the same as Schrödinger did for harmonic oscillator, if we do Darboux, but we will, if we do one Darboux and come back to the same potential operator shifted, then it's exactly harmonic oscillator, because it's f must be linear from this equation, and u means that u is quadratic. But yes. Which one? No. Yeah. This is finite gap theory. That's what I said. In that case, you have only 0, all right? Constant you have. But if alpha is not 0, then you have spectral theory, which is generalization of. So this is exactly the thing. So we have finite gap theory at the level when sum of alpha equal to 0. It's one-dimensional extension of finite gap theory in direction of harmonic oscillator. That's what I like a lot, because and in this direction you're losing completely algebraic geometry, because you're moving towards Painleve, right? So this is a kind of Painleve. Alpha is parameter of Painleve. So in the same way as Painleve-I, you can view this as deformation of elliptic function. That's the same here. And so this is Painleve-IV in this case. So we thought that why don't we consider the following, just version of maybe harmonic oscillator, which it's not just shifted up, but shifted also in x. Then we should have also maybe some peculiar deformation of harmonic oscillator with spectrum exactly like harmonic oscillator, because it's shifted potential will have the same spectrum, right? So you will have the same idea. And we spent quite a lot, and without success, probably we were looking for something, because we wanted to find solution which is, we didn't want to have analyticity, but we want to have existence on the whole line, and maybe continuous, for example. So that was the plan. That maybe, but we didn't find anything, and maybe the nature resists. There is no such thing, right? That's what we want. And at the same time, Grammaticus, Romani, and Moreira, they derive a class of equations using singularity analysis. And one of the families was generalization of this, right? So, and so this equation appeared independently in completely different as a result of classification of certain types of delay equation, right? So, and there is another interpretation Yeah. By the way, why we call it delay Painleve-I? I mean, because delay is clear because you have you relate function expression with f of z and f of z plus h or minus h, and therefore you every time you compute, you solve essentially Riccati equation, knowing with data in the previous one. So delay equation, of course, is very much different from usual ODEs, because for ODEs you have initial data numbers, right? In delay case, initial data is f on the interval from 0 to h, because then you solve and so on, right? And therefore, we tried to guess what is the right initial data, and we failed with John, right? But formally, you can consider this as how it is related to Painleve-I. The terminology usually in discrete theory of Painleve equation, we call discrete analog if you have continuous kind of limit to this. And if h go to 0, and if you assume this kind of thing, then if you go to h equal to 0, then for w, you have this, and after integration, usual Painleve-I equation. It does not necessarily help much because the limit, as you see, is quite tricky, which is often the case, right? But anyway, this is the name. So delay Painleve equation is this equation which comes as periodic closure of dressing chain, and our motivation was initially potential application in spectral theory, and it didn't happen. But just a second. Yeah, okay. Let's keep this. You can also, I will mention, derive this from intermediate long wave equation as some reduction, intermediate long wave. So it has at least 3 different interpretation of this equation, and it's related to Painleve, so we thought that it's interesting. So the first thing is that it has it can be written in conservation form, and this is the thing. I will use it so the integral, and indeed, if you differentiate this formally, then you will have exactly delay Painleve equation. There is a clever thing actually done. The only thing is that t minus 1/2, because it doesn't affect anything, but it's actually, you will see that this will be, this 1/2 is the same as 1/2 Riemann zeta function or Bernoulli numbers. This 1/2 is of the same nature. The parallel will be anyway. So we so what's about solution? We want to study solution of this. And when alpha is 0, which is finite gap case kind of analog, right? So when alpha is 0, we have plenty of solution, because let's consider period 2 functions. Then shift is involution, right? Shift by 1 is involution. By the way, h equal to 1 from now on. And then you can split is as period 1 function and period 1 anti-periodic function. That's so and it's clear that anti-periodic function satisfy this, because anti-periodic function clearly kill left-hand side, but f square is periodic, and therefore it's killed by t minus 1 by shift as well. So this is somehow obvious. So we have plenty of entire solution, and we were interested for entire solution in the whole complex domain. 2 pi periodic. So we have plenty of this, right? And we wanted to consider what happens if alpha, what happens with this solution when alpha is not zero, for example, for smooth, right? So the way we did was quite natural. Let's assume that alpha is very small and consider formal series solution, right? That's in alpha. And then we had this, let me just point it out. So let's introduce psi, which is t plus 1 phi. Psi will be t plus 1 phi. And then psi satisfy pure differential equation, but on the right hand side you have phi here, so it's still you have to solve to psi n. You have to solve differential equation, but in order to find phi after that you have to invert t plus 1 operator. So it's still non-local, right? But that's a kind of nice. And let me point out also this term, right? This is the key relation. This one, phi I, phi n minus y, should remind us kind of Catalan relation, which is I'm going to draw. So our result was that for any phi naught, you choose phi naught, and then you solving this. Then there exists formal solution with quasi-polynomial phi k. Quasi-polynomial means that it's polynomial in Z with periodic 2 pi periodic two periodic coefficient, 2 periodic coefficient. So it's kind of quasi-polynomial solution. And this is not difficult, right? And then we looked at, of course, the question is what happens. Convergence is still probably they are divergent, probably they are formal. But the simplest case choice was obviously, let's start from 0. So phi naught is 0, and then we have this relation. Then this is this relation. So the rest will be about this choice, right? So we consider 0 solution of alpha equal to 0 and consider perturbation in alpha, formal series. So then this will be phi n, phi capital now, and this is right. And now you integrate, and every time you integrate, you have extra constant. So this, in this way, we came to this interesting family of polynomials, which we'll call be phi n, z, and tau. Then there are many parameters tau because every time we have integration constant tau. Okay, so integration constant psi because we should psi, and psi is related to phi. Remember that t plus 1, so it's just sum of this, right? And this is how they look like. They polynomial in Z, but they also polynomial in parameter tau. It's similar to what happened to this rational solution of tau function of rational solution for KdV, and it reminds, but it's different. It's different from Bernoulli-Catalan polynomials, although it was kind of tempting to compare that. Anyway, so what's the property? The property is symmetry, but look at that. It's not quite, because tau we have to change to tau tilde, and tau tilde means that we have to odd times should be changed sign of times, right? So in the future, all our odd time will be 0, and therefore we will have symmetry. This symmetry, which is the symmetry of Bernoulli polynomials, right? This parallel, the claim I want to say, there is a parallel with Bernoulli polynomial, but leading coefficient they are not monic. Leading coefficient are Catalan numbers, and so this is leading term, and then next term is also Catalan numbers, but they depend also on tau1. If tau1 is 0, then it's anyway, it's n times power of 2 Catalan numbers, but it's just related to an. And this is a bit more complicated because it's involved also tau2, and this is the thing. Okay? So formula is written here only in assumption that tau1 equal to 0. They quickly become complicated. And so let me just say a few words about Catalan numbers. Arnold liked them a lot, and Stanley has a book, Catalan numbers, where he gave 214 interpretation, and we can supply a couple of more, I mean, easily, right? So this is kind of, and Stanley said that this is the longest actually input about numbers, Catalan numbers. But what I want to point out, you remember this is a recurrence relation. It's quadratic. Compared to Bernoulli numbers, it's linear, right? It's also non-local. You have to take all previous one, but it's quadratic. Okay, Catalan numbers are next after Bernoulli complication. But Bernoulli are rational. This one is integer, which is a kind of bonus. And this 1 minus 4x, it appears that's a generating function. It's square root of this. Now, funnily enough, it's not, of course, Catalan. Catalan is, you know, according to Arnold, all the terminology in mathematics, all the attribution are completely wrong. And it was known at least to Min Cantu, was a mathematician of Qing dynasty. And this is a book of 1730. And these are the numbers, I think 1, 2, 5, 14, 42, 132. So my PhD student confirmed that this is correct. I mean, the first numbers are precisely this. So this is from real book. So you never know whether it was the first, but at least it's about 100 years before Catalan. Right, but it's just the name so anyway. So we want to introduce what we call Bernoulli-Catalan polynomials and Bernoulli-Catalan numbers. And for this, we have to compute conservation law. We have now formal solution. It is unique. Well, it depends on parameter tau. And we computing the conservation law. And the right-hand side, oops. And the right-hand side is, so this, if you substitute here, and then you have to integrate, and the result, of course, is depend only on tau. So Sk are parameters which depend on tau. So you have very triangular transformation. So triangular means that Sn is tau n plus polynomial of lower. So this is a clearly invertible transformation called a fine Cremona transformation, and all the coefficients are rational, right? So this is S versus via tau, and this is tau expressed in terms of S, right? But relation is kind of complicated, right? But anyway, you have sk, let's call it tau k, is initial value of integration constant, and sk are integrals because it's conservation law, so it's value of integral some kind. And tau or tau k parameters, well, integration constant. Anyway, it's integrals, and this is okay. So, but they are quickly becoming complicated, and so we have at that point we had two natural choices, right? What to do with this, right? It's a polynomial depending on many parameters, and we had to choose to concentrate to study which are more important, right? Most important. And of course, the natural choice was let's put all tau to 0 first, and let's see. Then sk will be non-trivial. So these are, if you put all tau equal to 0, then we will have this kind of polynomials with some properties which remind, but again, it's rational, so it's reminds. Remember that highest, this is by the way 5, which is Catalan, and this is, it should be 14, but it's because it's a multiple here actually, so on. Anyway, so the highest coefficient of Catalan, the second one, but so this is, but the more significant, so, and there was second choice. If you have all integrals to be 0, sk to be 0, okay, then tau will be tau star, which we call Bernoulli-Catalan numbers, right? So, by the way, I should say straight away, you know, Bernoulli numbers have interesting properties. They, well, all odd equal to 0 except the first one, which is -1/2, right? Which is very important. And the rest one have sign alternating. Right? We have conjecture that it's the same as true, but we can't prove it because it's quite complicated relation, and this is the thing. By the way, I remember I've seen a book Japanese written by Japanese mathematicians for school children, and they wanted to explain Riemann hypothesis, right? And I thought, well, that's interesting. How to explain Riemann hypothesis for high school students? So, and then I look inside, right? And they basically saying about this about zeta function, and of course you cannot explain analytic continuation. That's a problem. And they said that, well, it's so the problem Riemann hypothesis is about position of zeros of this kind of function, and why we think that it's a difficult problem, right? Riemann hypothesis is a difficult problem because they said that we know the values of Riemann zeta function at integers, and they expressed in terms of Bernoulli numbers, which are the most complicated numbers in mathematics. I love this because to me it's maybe not, well, first of all, it's complicated, it's part of being rational. Second, is probably one of the most important indeed. And actually this formula, computation of Euler, as a corollary, because zeta of even function are positive, obviously, and you have -1 to the n times Bernoulli in Euler formula, this is the proof that Bernoulli numbers alternate. I don't know if there is easier proof, but here it's missing, right? We don't know this, but our conjecture is that they will continue alternate. We computed for a while, but anyway. But it's a kind of complicated version. Why? So first of all, yes, and Bernoulli-Catalan numbers. Now Bernoulli, what is Bernoulli-Catalan? It should remind us Catalan relation, of course, right? But there is K here. and K is not coefficient. It's actually pseudo-differential operator. I mean, it's infinite, right? And it's just 1 over T term, T half, where D is D by dz. So this is a kind of thing. Now let me remind you that this is a polynomial, so this is well defined. Right? But here the coefficient are Bernoulli numbers. So this is why we called it Bernoulli-Catalan, because this relation is Catalan relation, and K is made from Bernoulli now, right? So this is quite complicated, but this is the and this is how they look like, and this is actually the main, maybe the main byproduct of our work is that this sequence of polynomials, which we believed that it's important, but didn't have a justification for this until recently, until DeYoung talk, actually, which I attended online. And then I saw something in his talk, accidentally, something which is related to. And that's how I was going to talk about. So you have two polynomials. Remember, S tau equal to 0 or S equal to 0. Qualitatively, they are very, very similar, right? So, and actually, before this relation with Masur-Veech volumes, which I'm going to explain, I was personally in favor of phi, tau equal to 0. But now, because of this relation, S equal to 0 is more important. But if you look at the graphs, then you wouldn't distinguish them. They are qualitatively very, very similar. So it's phi is when tau equal to 0, and Q is Bernoulli-Catalan is S integral equal to 0. Okay. So this is the property. They have property of Bernoulli numbers, symmetry, and these are Bernoulli polynomials, right? And we can say we can define leading coefficient, and they expressed in terms of Catalan numbers. You see, plus something. So. And this tau star, it's simply values. It's similar to Bernoulli numbers. So Bernoulli polynomial has a property that Bernoulli bk prime equal to n times bk minus 1, right? So you k times bk minus 1. So therefore, every time you have one constant of integration, and Bernoulli was clever to determine this constant to be Bernoulli numbers, right? So here it's a similar situation. So we have to find this UK. So for they equal to 0 for k odd automatically, but for even, which is the most essential, is twice value of this. And you see that this is so this is the case of Bernoulli numbers, and these are Bernoulli numbers minus a half. That's the only one odd non-zero 1 6. That's a famous calculation of Basel problem by this. Then 0 minus 130 0 plus 142. The next one is again minus 130. But they are the thing. And the relation you can write down as integral also this, and this there is a similar relation for Bernoulli numbers. So this parallel with Bernoulli polynomials is quite substantial, but variation is very, very, I wouldn't say that they're similar. It's just something of, there is a common property, but they are very far from each other. But Bernoulli-Catalan numbers and polynomials are much more complicated because it's quadratic. It's non-linear recurrence relation for Bernoulli-Catalan numbers. And this is the thing. Okay, so why it is important? And that's, at this moment we were 2 years ago, and then only when I listened to Zhang talk, and this was talk about calculation of Masur-Veech polynomials, which was done by Youjin Zhang from Tsinghua, Don Zagier, and Zhang. And then when I saw one of these equation, which is explaining the relation with delay Painleve-I. So what's the question? The question is, you consider moduli space of algebraic curves of genus G with n marked points, and its cotangent bundle is a pair, a moduli space of pairs C and Q. Q is quadratic differential on C with simple poles at marked points. Okay, so this is cotangent space to the famous space MGN, modular space of algebraic curves with marked points. And we want to compute volume. Now, volume, of course, of cotangent bundle is infinite, right? So you have to make sense of this. And that was done by Masur and Veech, and it can be done like this. You can you have quadratic differential, you have flat metric. Define a flat metric, which is no modulus of Q, which is flat metric with conical singularity on the curve, and finite area. So every area of the corresponding, although Q have poles, simple poles, the pole is something like 1 over R. When you integrate volume, it's the integral is convergent, right? So the area will be finite, right? And you do the following: you take the part of cotangent bundle, which is subset of when area is less than 1/2. 1/2 is cleverly chosen, and I don't know who was the first. The story is before the people I mentioned, but Kontsevich and Mirzakhani participated in this calculation because it's related to Teichmuller space. But anyway, so then you have a kind of tube around modular space, right? You take only volume is fixed, right? And then you compute volume. And volume you compute as symplectic volume because you have canonical symplectic structure. So you compute as symplectic volume. And there was a conjecture of Kontsevich, which was proved by Asrieskin and Zorich, and then many other development. Now I learned this from mainly from this paper by Zhang, Don Zagier, and Youjin Zhang, but actually, as I said, the story goes back to Kontsevich, who was able to guess the answer for G equal to 0 for genus 0 case because it's simple. I don't know actually how he guessed it, but Maxim, of course, can do many things. So that was probably based on, I don't know. But anyway, this was proved later on. The formula is quite simple. It's powers of pi divided by powers of 2. Very simple, misleadingly simple formula, but this was nevertheless non-trivial to prove. And then next step was done by Chen, Mueller, and Soulager. And they rewritten the corresponding volume. They made a link with the story which was very well studied after Witten, as Witten conjecture and Kontsevich theorem, calculation of characteristic numbers of moduli space. So you have this canonical psi1, psi-n first Chern classes of line bundles, which are at each marked point, you have cotangent bundle to the curve. And that gives you line bundle of the moduli space. You take Chern class, and this is called psi. And this is to form, and you can take product of this and then integrate this. And if there is no lambda j, that would be the story of Witten, because Witten said that corresponding numbers are described by KdV hierarchy. KdV hierarchy describing this this integrals, right? With you should consider KdV hierarchy with initial value u equal to x, and this is a kind of thing. It was, you know, KdV is with such initial data is out of classical spectral theory, right? You have to but fortunately you don't. It's not about spectral theory. After Witten, KdV hierarchy became machinery to produce formal series. You substitute and you expand it as a series. You have recurrent simulation, and this way you can find all the characteristic intersection numbers, right? And but here they had lambda j. Lambda, what is lambda j? Lambda j. There is also another line. It's not one bundle. It's vector bundle of h1 of the curve. You have h1. You have g holomorphic differential, and g dimensional space. It's called Hodge bundle, and this is g dimensional. And you can take lambda are corresponding Chern classes of this n dimension, right? And it's linear in Hodge lambda j. And this is so what happened as Youjin Zhang explained to me that Chen explained that showed this result, and of course at that point it became clear that now one can use the power of theory of you know, Dubrovin-Zhang hierarchies, because there was a paper by I will give a reference later on. But anyway, so let me say now. Let's define. I'm going to describe now what De Young, Don Zagier, and Youjin Zhang discovered, which is quite beautiful. So let's consider Masur-Veech, which is generating of essentially AJN is essentially volume. It's just scaled by certain powers of pi, certain factorials, powers of 2, they all over the place. So this is, if you think, it's scaled of volume. So AJN is essentially volume. It's volume times known coefficient. Okay. So this is AJN is, and we consider generating function. And you have two parameters, two numbers, G, which is a genus, n is a number of marked point, and you have x to the n and epsilon to this. It's a kind of notation I'm using from paper of Young, Zagier, and Zhang. And you see it's yeah. So they proved that Masur-Veech free energy satisfy this, and this is actually where it which reminded our delay Painleve, and indeed this is actually form of delay Painleve equation. And anyway, yeah, the proof is based, of course, on Chen, on Buryak, because Buryak also considered Hodge integrals involving lambda, and Dubrovin, Liu, Yang, and Zhang paper in 2016. So that was also kind of very important link between two problems: calculation of Masur-Veech and the story of Witten and Kontsevich and all this. So this is a very remarkable achievement. Why? Because it gives us recurrence relation, right? I mean, this is so. Let's essentially it's so what was that? H was Masur-Veech energy, and let's define F, which is this shifted H, and shift as well. I mean, this is a transformation, which is a kind of, and that's our result essentially follows immediately from YZZ by comparing our delay equation with equation from Young, Zagier, and Zhang paper. So it turned out that this formal solution we studied is exactly related to this calculation, right? I mean, this is in particular this tau star parameter. They are linear combination of Masur-Veech volumes. Okay, and actually, in the paper of Yang, Zagier, and Zhang, there is another recurrence, another equation, which is differential, and from this equation we have this recurrence relation. And I visited Yang recently, and he actually pointed out that you can use, so this equation uniquely determine TL star. So the second equation, which we kind of initially underestimated, actually a very useful complement to delay Painleve, because delay Painleve you have in principle arbitrary tau in principle. So, but if you use the second relation of de Young, of de Young, Zagier, and Zhang, then you have this uniquely defined this T L star and for QL, right? So this is these Bernoulli-Catalan numbers are real, and yeah. So this is as a corollary we have for G equal to 0. You remember these Catalan numbers, and in that case we have A0 n like this, and if we remember that it's multiple, this is multiple of A, volume is actually multiple of H-man, and this is, and after, if you open the bracket here, you have this Kontsevich form. Right? I mean, this is, so you see that it's quite, I mean, a remarkable constellation. It's a remarkably simple formula as a result. For G equal to 1, it's more complicated. And but this formula is known. Actually, I don't want to pretend that we invented, we derived new formula. All these formula were in essentially, we just it's interpretation of results of de Young, Don Zagier, and Youjin Zhang. So, but it's a kind of nice application of what we did anyway for this, and Right. So, right, natural question. Natural question. So, discrete Painleve, how it is related to discrete Painleve? So, so there is discrete Painleve-I already exists in the literature, and actually it's quite remarkable. This is, to me, this is the first and maybe the most important appearance of discrete Painleve in mathematical literature, and this is in the work of Shabat, right? So this is the story of orthogonal polynomials. So you take a weight, which is sometimes called Freud, but I don't like terminology because Freud is 1970, Shabat did it in 39. Anyway, it's natural anyway. You take just quadratic exponential of minus x to the 4, right? Rather than minus x squared, you take minus x to the 4, and you have parameter t here, right? And then the question is, then Shoha, right? So what's the question? So every you have weight, and you have three-term recurrence relation, right? So basically, the problem is if you know the weight, how to find coefficient and recurrence relation, right? And of course, there is a general formula, but for this you have to do some general things. So in this case, Shoha said that there is better way to produce this. So this is actually three-term recurrence relation. All what you have to know, you have to find this coefficient. Okay, and this coefficient should depend on t, right? And he said that the best way to find this coefficient is by this nonlinear discrete recurrence relation. This is the way to find coefficient in three terms recurrence relation, where A is a quarter, B is 0, and C is t. It depends on t. Right? This is so. If you want to put 0 here, then put c equal to 0, and then it will be just e to the minus x to the 4. And this is a kind of first discrete Painleve. And natural question. So we have a kind of delay Painleve-I. So this is discrete Painleve-I, and I don't know how many discrete version of Painleve-I we have, but this is probably historically the first and most significant one. Magnus, I think, was found the relation to Backlund transformation of. There is this Painleve equation. They interrelated with each other actually, so it's difficult to distinguish sometimes, you know, one Painleve from another. So this you have Backlund transformation for fourth Painleve, which was just a second, which appeared actually in dressing chain. You have two parameters here, alpha and beta, and they are related to parameters in dressing chain. Actually. Anyway, so this and if you take corresponding function xn of t, t is this t, and if you have this t, then it satisfies the Painleve equation. So there is a way from discrete Painleve equation to delay, but it's quite tricky. It's it was done by people like Magnus, essentially. I mean, this is the thing. Anyway, so finally, I'd like to mention that why delay Painleve equation another origin, and this is there is a fundamental intermediate long way equation which interpolate Korteweg-de Vries equation, which is shallow water, and Benjamin-Ono, which is infinite depth. So there is a parameter d here, and depth, and t here in this is shift also, but in the imaginary axis, so id, and this is so this was written by Joseph, but in integral form, in this form, it's Chen and Li, 1979, and it was studied by Kadama, Bloit, Satsuma, and John Gibbons and Boris Kupperschmidt at the time. So it was quickly recognized as one of the significant, and it's obvious by if there is integrable way between two famous equations, it's clear that it's significant, right? So this is and if you substitute this substitution, then you have the delay Painleve-I. So it's certain reduction of this equation, and because of result of John Gibbons and Kupperschmidt, we have a kind of Lax pair. So this is probably if we want to study this relation, which we did not, of our theory with intermediate long way, we should use this result from integrable systems more, you know, this Lax pair. And just a few questions. So one, as I said, so we introduced these Bernoulli-Catalan numbers. Their recurrence is complicated. So what's the meaning of them? Any combinatorial, maybe what they are for, what they're important for, and is it indeed alternating? Why they're alternating? And the combinatorics is, so there are actually Qt Catalan numbers, kind of Qt version. You may say that it's not related, but there are deformation of Catalan numbers which are completely different, of different nature, and probably even more important, but they're different. So we saw that Q are related to Masur-Veech calculation, but phi when tau is 0, or for other values of tau, maybe they're also important. And the convergence, or there are some outstanding conjectures about large genus asymptotic for Masur-Veech, particularly mentioned in Young, Don Zagier, and Youjin Zhang paper. And this is completely open. Probably this form of series divergent, so you have to do some analysis in order to, if possible, to apply this. And just the last thing, there is a Q version. There is a Q version, and of delay Painleve-I, and this delay version, Q version, was studied analytic property by Shabat for modulus Q smaller than 1. For modulus Q smaller than 1, there is analysis, and especially deep in this paper by Liu. So Shabat started this, and Adler, Seva Adler continued, and Liu, I think it's his PhD in Cambridge, studied this in more detail. So for Q version and Q smaller than 1, we have some analytic result, but as soon as Q is 1, in our case, kind of Q equal to 1, everything seems to be divergent, formal, and therefore that's it. Thank you.
Okay, thank you. Questions?
Yes. No, only recurrence. And recurrence is quite complicated, right? I mean, it's this is so this is what is it? In principle, here it's like maybe even so. Look at this. So this is polynomials, right? Which is a kind of, imagine that you have Bernoulli polynomials, then you can recover Bernoulli numbers as value at 0, right? Bernoulli observation is remarkable that if you know values of 0, you can recover the whole Bernoulli polynomials by a general form, right? So it's enough to know here. So here it's a bit, so at least originally, this is Catalan relation. It would be simple, but there is this K, right? Which is, as I said, expressed in terms of Bernoulli numbers, right? So, but in principle, this, if you know already Bernoulli numbers, then it is, you can find Qn of Z, and then you can take values at 0, half of this. That would be Bernoulli numbers, values of 0. Yes, yes. Triangulation is my favorite interpretation of. Yes. This is quadratic. This is intrinsically quadratic. So this could be related to, you know, to different delay Painleve equation, because we consider, I don't know which one, but so we consider the simplest one, right? Which is and if you remember, this is it's quadratic. It's like first Painleve is second derivative is u squared plus x, right? But you can, in principle, consider what is Painleve 2, or what is cubic, for example. One can consider delay version of other Painleve equation. This equation we were mostly interested in, and this is quadratic, like first Painleve, and all the relation are the 4 Catalan type. No, this is already all S parameters sk equal to 0, all integral size 0. That's what Bernoulli-Catalan. So tau, therefore, uniquely defined. And they have this form, and this is what we call Bernoulli-Catalan numbers. So they already fixed. It's like Bernoulli number. Bernoulli polynomials, for example, you can define them by two relations. You can say that derivative of Bn is n times Bn minus 1. And you can say that difference of Bn is n times x to the minus n minus 1. And these two define Bn uniquely, but you have complicated it. And the same here, we can use two relations from Diane, Don Zagier and Youjin Zhang to define, but it's more complicated, basically. Yeah, I mean, so these are, where is it? Right. No, I mean, it's I had this one. So there is another recurrence relation, which is this. And from this recurrence relation, in principle, in combination with delay, that's actually Diane explained to me, that probably the most effective way to compute these numbers is using combining our delay Painleve-I and their second relation, and alternatively, and that should give probably effective way. But whatever you do, it's tricky.
Okay, more questions? If not, let's thank the speaker again.